Hi, this is our Structures 1 project on the Great Spaghetti Bridge Challenge. Franz, Jake and I, Costa, we're in Group 17. This video is aimed to show our planning, construction and analysis on our two spaghetti bridges. The objective of this challenge was to construct a spaghetti bridge that would withstand the largest load. The constraints and limitations of this project were to only use spaghetti number 3, super glue, make a bridge that spanned 350mm, and with no greater dimensions than 80mm and weight of 200 grams. Our first design was very simple, taking the form of a king post truss bridge, like the one shown in the bottom left hand corner. We picked this as it's simple and would weigh a small amount. The bridge shown here is Sauk Creek Bridge, located in Port Washington. It shows a good example of how the supports will work. We used a 30-degree angle as the top chord pitch, and these are the trigonometry equations that were used to determine the length of the king post and the diagonal members. The next photo shows our workings of how much force each member will experience. There were many difficulties constructing the first bridge, as the glue wouldn't stick and it was difficult to make accurate measurements. This photo shows glue and the truss member. This photo of the first bridge, this was slightly poorly constructed but demonstrated a basic shape of the diagrams we had made. The bridge weighed a total of 140 grams. Our first test was completed from my house and I labelled the weights that were used to complete the test. The bucket weighed 500 grams and each bottle was 1500 grams. The bridge held just under 5 kilograms, so I estimated the maximum capacity to be 4.8 kilograms. The bridge held just under 5 kilograms. This equation shows the ratio between the weight and maximum capacity. It can be said that the bridge held 34.28 times its weight during the experiment. This photo shows where the bridge broke, being at the top on a compressive member. This subsequently led to the failure of the bridge. The diagram shows where the bridge failed. Through careful redesign, we believe the bridge needed more webbed members. These are named chords. The Howie girder truss was used for this as it was an effective design. This image shows the length and angles used to construct the bridge. This 3D program gives a good look at what the bridge will look like in 3D once constructed. When constructing the next bridge, we used an angle grinder to cut the ends off the members. This gave a nice smooth mounting surface. This picture is of the final product. The bridge weighed a total of 180 grams and looks significantly nicer than the previous trial. This photo shows the bridge set up on the apparatus at the City East campus. This video was the final competitive run for our bridge. The aim was to spin the wheel until failure, and the tension gauge gives an accurate measurement in both kilograms and newtons. The tension gauge was located just below the video. The slack had to be taken off before tension was applied, as you can see in the video. Our bridge held a total of 19.5 kilograms and was the third strongest bridge calculated by ratio. Around about now is 5 kilograms. Here's 10 kilograms. Here's almost 15 kilograms. And around about here is 19.5 kilograms when the bridge snapped. This photo shows the point at which the bridge broke. This member was a tension member. We used 20 kilograms for the sake of an even number for workings. This photo shows the workings for bridge number 2's ratio. This photo shows the ratio between the two bridges. it can be said that bridge number 2 was 3.24 times stronger, or was a 324% stronger. To conclude, we successfully learnt about trust types and bettered our results using a multitude of resources, these being 3D digital testing, hand drawings, hand calculations, multimedia calculations, trial and error, and external sources. Thank you.